Hi, and welcome back to Hands-on Problem Solving with Machine Learning. We're in the sixth chapter, Diagnosing Issues with Models. In this video, let's try to understand our accuracy in predicting numbers and see how we can debug our models. So the rationale for this section is a lot of times you would follow a tutorial or otherwise follow some documentation to test out a new model. And often the model would spit out a prediction like what we've seen in the last few videos, where we basically train a model and they give us some accuracy or some scores and whatnot. And it's actually quite hard for you to figure out what the score means. Why did a particular model predict a particular number, and how did that sum up to give you the score that you're staring at? So in these few videos, for the last part of the course, I want to try to give you sort of an overview of how we can go on diagnosing issues with different machine learning models. So let's first look at the problem of regression. So again, regression is about predicting numbers, and we are trying to understand our accuracy in predicting numbers using machine learning models. And so to set up the situation, what we're doing here is we are first in in6, again importing the Boston dataset by calling the load Boston function in the scikit-learn.datasets module. And we call the load Boston function to get the data into Boston data, right? So after the data is in the Boston data, what we can do is we can then, in in7, split this data into its inputs parts and the output parts. So basically, x, uppercase x, is our inputs, and lowercase y is our outputs, right? So very much like the convention. In in8, we import a very typical linear regression model from the scikit-learn linear model package. In in9, we instantiate this model. And then, as you know, from in10 to in12, we fit the model using a training and testing splits. So it allows us to correctly use our data sets so that we have reproducibility and we also don't overfit and waste data. So one of the first issues you would see is if in 13 we compute the score of the model, then what happens is you will see a model score that is 0.739, which really means relatively little, and as you can see, probably depends a lot on how the data set is split around X train and Y train, right? So imagine if in the train test split you have 1,000 data points, and what happens there is, depending on how you segment the 1,000 data points, especially if your training set is quite a small proportion of your entire data sets, your model score will be very sensitive to the way that your training and testing set is done. And also, the other thing that is impacting your assessment of the quality of your model is that you now have to then take the model and score it against the test sets instead of the training sets, and you basically don't have a good way to sort of further test your model after it went through a few iterations of the testing and the scoring mechanism. So one of the things that we can do is to do k-fold cross-validation. And so we've seen this before, and this allows us to take our training sets and further splits it into, I guess, sub-training and testing sets. And so we can split it 5 times in different ways and compute our score across all 5 folds. And so the effect of this is it allows us to collect sort of a distribution or sort of a list of model scores across different splits of the training set. So the benefits are twofold, right? Number one is we know the spread of the score in addition to the average, and we also can now properly split test our training set into further sub-training sets and sub-testing sets, right? So here in 16, I'm computing the mean of the score and the standard deviation of the score, and it shows us that the mean score of our current model is at 70.8, and the standard deviation is about 0.08, right? And we can import various metrics from scikit-learn to really understand these scores further, right, and understand the model's prediction power further. So in 19, what we have is the explained variance score. So it's very easy, right? So if you have a data set that is distributed across, let's say, a range. So for example, in the Boston house prices data sets, that the prices are distributed between 10 to 50,000, right? And so the explained variance score roughly tells you how much of that spread or that variance or that variation in your data sets has been explained. So this is a slightly different metric than simply a loss of how accurately you have been predicting the prices, but more how much of the noise and the variance are you capturing, right? So if you capture the more variation and the more of the variance you capture, the more of the whole story you're explaining using your model, which is better. You can also do something like mean absolute error, and the definition is very simple. I've put this here in the comments, and basically you're taking the actual value of the testing sets and the predicted value using the testing sets, taking the absolute value of that and computing the average, right? So situations where you want to use this is when the mean absolute error is a good measurement of how your model sort of creates cost and benefit in real life, right? So here we can see that 3.15 is where our mean absolute error lies. A very similar application or similar metric is the mean squared error. Again, I've put the definition here in the comments. And so basically you are taking the true y and you're subtracting the predicted y. You're squaring it and then you're taking the average. So the idea here is if you square a number, then a small number will remain small, but a larger number would get exponentially bigger or bigger to the second power. So it penalizes large errors in your model. And so the model is allowed to make small errors across the data sets, but any large errors on an individual data point is going to be penalized. And then obviously you have median absolute error, and difference here is instead of having the average of the absolute error, you're taking a median, and basically the issue here is you will lose your sensitivity to large outliers in error rates. So if you have extremely large errors here and there, then median absolute error does not pick this up. The good thing is you can not be affected by these error terms and simply find and minimize the median of your error distribution. The last one here is from the R2 score. So if you're an Excel user or you've done any sort of traditional statistics, this is likely to be very familiar to you. In a machine learning context, this is simply a measure of how well future samples are likely to be predicted by the model. And so here, for example, we are predicting 72.5% of the R2 score, and you can see that the R2 score is actually quite close to the explained variance score, which roughly does the same thing,